Okay, so today we're going to be looking at another work problem. In this case, we're going to be looking at how we can calculate power, where we know that power is a function of work over time. So what we can begin here is we have a car delivers an average power of 100 horsepower to the road, and this weighs a total of 1.2 tons. And we're asking in this problem, it's asking how long will it take to go from 0 to 60 miles per hour. So there's a couple things that we need to initially do. First thing is the weight at 1.2 tons can be converted by multiplying by 2,000 pounds per ton to obtain 2,400 pounds. So that is the weight that the vehicle has. The other portion is the final speed, or final velocity that we're going to have is rated at 60 miles per hour. If we multiply that by the 5,280 feet per mile, and we also divide by the 3,600 seconds per hour that we have present, we obtain a conversion that gives us 88 feet per second is the converted speed that it's traveling with. So now that we have that, we can return to our conservation of energy aspects and our relationship between work and energy to find that work, again, is equivalent to a change in kinetic energy. And if we want to, we can also include the idea of a change in potential energy. Now we're going to assume that in this case, the car is going to stay on flat ground, so we're going to say that there is no change in potential energy. That being said, now, as a result, again, our initial kinetic energy is also assumed to be equal to 0 because we're told that it's going from 0 to 60, so we have a 0 velocity to start with, so as a result, our initial kinetic energy is also equal to 0. So our work, as a result, is simply equal to our final kinetic energy, which is 1/2 the mass multiplied by the final velocity squared. This, as a result, tells us that the work done is equal to 1/2. Again, the mass is 2,400 pounds divided by our acceleration due to gravity, which is 32.2, since we're looking at a US customary units problem. And our speed velocity final was 88 squared. This gives us a calculated value of 288,596 foot-pounds of force, or of work. Now, if we're looking at this idea, we're able to now look at the idea that this is what we need to have produced. This type of work needs to be completed. So what we're able to do now is express the fact that if we're able to provide an average power of 100 horsepower, the last part that we want to come back here to conversion factors is the fact that we have 100 horsepower. If we multiply that by 550, that gets us into foot-pounds per horsepower. And so we obtain the 5,500 foot-pounds as a result. So, per second, per foot-pound. So we have foot-pounds per second as a result. With this 55,000, we're able to now go with the definition that power is equivalent to the work divided by a change in time. As a result of this, we can plug in and express the fact that the power that we desire to deliver is 55,000. That needs to be equal to the 288,596 over the delta t. If we rearrange this, we find the delta t is equal to just over 5 seconds, so 5.25 seconds to be exact. So this allows us to see how we can relate power to work.